Hello everyone, welcome back. We are doing 2018 GATE question paper, and this is the last 5 questions of the organic set, okay, of the organic part. So the first question, which happens to be question number 30 in the set which I am doing, the first question says the major product formed in the following reaction sequence is. So you have a tertiary butyl here, and you have a ester group here, and you are having another ester group here, and you are putting trifluoroacetic acid, and then you are putting BH3, that is diborane. BH3 doesn't exist as BH3, it always exists as dimer, that is B2H6, and is a reducing agent, right? So first thing is we are adding CF3COOH. So you know CF3COOH will be much more acidic than your acetic acid, because 3 fluorines are there. So fluorines are very electronegative. So if you remove the proton, you get negative charge on the oxygen. That will be stabilized by resonance as well as induct effect by this this fluorine, and therefore it is very strong acid, and it will be used for hydrolysis of the ester. Now this ester is quite stable. You have to boil in aqueous acid, but this, when tertiary butyl is there, this tertiary butyl is waiting to be left out, because it's a very bulky group. It is waiting to leave, and it hydrolyzes immediately in presence of strong acid, something like trifluoroacetic acid, and therefore the oxygen of the ester goes and attacks this proton. See, the mechanism of ester hydrolysis of tertiary butyl ester is very different. Generally it is always attack on the acyl. This one is alkyl cleavage, okay? So you can see the mechanism how it happens. First oxygen attacks the proton, you get positive charge, and this one leaves it by SN1 mechanism. Alkyl group leaves. There is no attack on the acyl group, right? And this group leaves, and this will go and this will be attacked by the anion, and something else will be formed. But basically this leaves, and you are getting acid, right? So ester, when hydrolyzed, you get acid plus alcohol. So here this part, the acyl part becomes acid, and that's what we get, and that is what is of interest to us. Next step, what happens? Next step, you are adding diborane, BH3. So important thing is you are adding only one equivalent of BH3. Now BH3 reduces, but it reduces not as a nucleophile but as a electrophile. Generally, something like NaBH4. So what happens in NaBH4? You are having hydride, BH minus, so it goes and attacks, and that's how hydride gets added, and addition of hydrogen is reduction, and that's how reduction happens. Now if NaBH4 is there, it will reduce very happily aldehyde and ketone, because they have lot of positive polarity here. But with great difficulty, very slowly it will reduce esters, but it will never reduce acid. Why? Because acid, as soon as this proton goes, you get negative charge. This negative charge is coming here, and then it goes here. So lot of negative charge on this carbon, right? And therefore H minus to approach here, it becomes very tough, because negative will repel. Exactly reverse of that happens when you are using BH3. Now BH3, it is a Lewis acid. BH3 accepts lone pair of electron. So what happens? So whichever is electron rich, they will attack first, and which is electron deficient, they will attack slowly. So we saw acid is more electron rich, and therefore acid gets reduced, and ester is not at all touched. So if you are doing reduction in presence of diborane, if you have carboxylic acid, amides, esters, and aldehyde ketones, remember aldehyde, ketone, esters, all this will remain untouched, because they have quite a lot of positive polarity. They will not be able to attack this diborane, but only thing which will attack and get reduced is amide and acids. Amide also, amide has lot of electron density. Why? Because nitrogen is there. Now nitrogen is less electronegative than oxygen, and therefore it pumps electrons and increases electron density here. Whereas ester is not able to donate electron that very well, because oxygen is electronegative, so it does not share electron very happily, right? And therefore very clear it is from after this step that reduction will happen on the acid and not on the ester. So the acid will get reduced to alcohol, and amide will remain as it is. All that I said is written here, you can read it. Yeah, so this acid will get reduced and becomes alcohol. Similarly here also it will get reduced, becomes alcohol, and then transesterification can happen if it was close by, but you can see they're quite far, and because of this double bond rigidity is there, so reaction stops here, and therefore the product you are getting is D. If it was more feasible, if it was more close and this rigidity would not have been there, happily it would have found 5-membered ring, because intramolecular transesterification is very common, right? So the product is D. Now the major product of the following reaction sequence. So this this one is there, you can see what is this. This is vinyl halide. This is another vinyl tin tributyl tin vinyl group here, and in presence of PDPPS34 and that is the first reaction which is happening, and second reaction it is just heating up in toluene. Toluene, as you know, is non-reactive, so it is a solvent. So let's see what happens. So first step now, this is called as Stille coupling. So if you see in the reactant, this part is not needed in the beginning. What we need is vinyl bromide, which is reacting with your vinyl tin complex. Now what Stille coupling does is, it basically couples up aromatic and vinylic system, aromatic and aromatic system, or vinylic and vinylic system. So here it is coupling both the vinyl group. How it happens is very interesting, same like how Heck reaction goes. See, these reactions are very important, and its mechanism is tough, it needs a lot of practice. You practice this, with this you will be able to solve a lot of other things also. So we start with this, palladium tetraphenyl phosphine. So this is 18 electron system, not at all reactive. So first thing what happens is 2 of the PPS3 will leave and becomes 14 electron system. Okay, it is still 0 complex, still it is PD0, but PD PPS3 twice. So it is PD0, and this vinyl system will go and attack, and it goes and forms complex here, and Br comes here. Now it becomes 16 electron. Now this is called as oxidative coupling. Why oxidative coupling? Because initially it was PD0, from here it has become PD2. It has become PD2, right? And then what happens? Then you are adding this tin complex. What happens is called as transmetallation. So this will also go and form a complex with this palladium thing, but bromide will leave. So this will basically go and attack here. This Br gets out and it forms SnBr Bu3. So this goes and form complex. Now you see they are all very close to each other. So now coupling becomes very easy. Straight away next step, this goes and forms bond with this, and so very rare reaction of vinyl coupling happens in the next step. That is, next step is reductive elimination, and you get back your PDPPS34. Next step is very simple. You can see here toluene is there, you are heating it. Toluene will of course not reacting. Heating means something like Diels-Alder should happen, and that's what happens. You can see here this is the diene part, this is the dienophile. Dienophile is simple alkene. Why it is called dienophile? Because it is phile, loving. It loves diene. Basically it reacts with diene. Diene means 2 alkenes are next to each other. And another important thing is, homo of diene, that is highest occupied molecular orbital, so which has electron. So electron donating group helps it, and electron withdrawing group will favor the reaction on dienophile, because LUMO is lowest unoccupied molecular orbital. So it is the vacant one which will attack, and we have to now till now it is very simple, but what basically they ask is regioselectivity. So something like you understand this, diene pumping group favors. So if you have some pumping group, so it will pump electron, so it goes electron here, it goes electron like this. So first attack happens here, okay, and this determines the regioselectivity. And in the withdrawing group, when withdrawing group is there in the dienophile, they pull the electron, so this they make vacant, so this part will react only with this part will not react with this, okay, because it is withdrawing electron, so you are getting positive polarity, and we saw it pumps electron, so here negative polarity was there, so negative will attack the positive, negative will attack the positive, and therefore reaction happens like this, and this will go here and this will come here. That's what determines the regioselectivity. So same thing is happening here, this comes here, this goes here, this comes here, and you're getting this. So here also you are having this basically CH2, this pumps electron through hyperconjugation. Nitrogen will more of withdrawing group through sigma bond, unless some resonance is there. Nitrogen actually does not pump electron through sigma, it pumps electron only through pi bond. So nitrogen role we don't have to consider, we have to consider from this CH2. So this pumps electron, this comes here, and this withdraws, so this goes and attacks here, and you're getting this. So if you look at in totality, the molecule will be, there is one more CH2, I missed it, okay, please be careful about this, yeah. And so if you look at here, so this one goes and attacks here, this goes attacks here, you get this, and you're getting this product. So the answer is D. Moving on to the next reaction. So they have given you molecule, and they are reacting with paratosyl OH. So basically it is paratoluene sulfonic acid. So it is a very strong acid, and 50% aqueous dioxane, and they are asking the major product formed in the retro-aldol reaction. So what is retro? Retro means you have the product and you go back and you try to find out, you simplify and you try to find out the starting material. So it is saying aldol reaction. So basically this molecule is a result of aldol reaction. So we have to find out what is the starting material. Little bit I'll revise aldol reaction. So aldol reaction, simple aldol reaction you will have studied in your from your school days. So you have an aldehyde which has carbon, alpha carbon, which has hydrogen on it, very important. It could have been ketone also, but basically on the alpha carbon hydrogen is needed. That's the first important step criteria for aldol reaction. So you put a base, you get this is the product. So how it happens is, if you put a base, this proton is lost, because one of proton, if it is lost, you get a negative charge, and negative charge is stabilized because of conjugation, and therefore it was a bit acidic proton, and therefore this one is formed. Next step, what happens, this negative charge goes and attacks on the next molecule, and you are getting beta hydroxy carbonyl group. That carbonyl group is intact. So on the alpha carbon, the proton was lost, you got negative charge, that one attacked the carbonyl group, and that carbonyl group becomes OH, so it is in the beta position. So you basically look for beta hydroxy carbonyl group when you look for the retro-aldol reaction. So here this was the ketone, so you have to look in the alpha beta position. So this is alpha and this is beta. Can you see hydroxy group? No, it is CH2OH. What we need is OH. Whereas here if you see this is the carbonyl alpha on beta. On beta you have OH. So basically this is what is happen where the cleavage will happen. So if this is the ketone, so mostly this should be the alpha carbon from where proton would have been lost, and that negative charge would have attacked here on which carbonyl group was there, which comes up, and you are getting OH, right? So that's what is happening basically. So you break up here, you get carbonyl group here, and here this is the carbon alpha carbon from which proton will be lost. So this is what is the retro reaction. So base takes away this proton, you get negative charge goes and attacks on this carbon, and you get this product, right? So this is what is happening. So let's see, because in molecule in the reaction answers they asked for stereochemistry also. So let's not disturb the stereochemistry and do the reaction. Okay. So what we look here, see here, this part is up and this H is coming out, correct now? So if H is coming out, that means it is towards the viewer, so it will remain towards the viewer and something else will go behind, right? Here also you can see this is behind, this is up, so which is behind will be away from the viewer and which is up will be towards the viewer. And this also, actually, if you see this hydrogen, no, this exo position is coming out, so it will be towards the viewer and the rest part will break up. So you are breaking it here, correct now? So you are breaking it here and you get this product. So basically when you break here, let us look at the stereochemistry. What has happened? This was top, we saw in the starting only, this was top and this was down. So this will be towards the viewer and this will be away from the viewer. Similarly, this H will be towards the viewer and this whole part which is broken, this will be away from the viewer when you are drawing in planar structure. So that's what I have done is I have just given the numbering here. I have just given the numbering here, so you can see here it was 1, 2, 3, 4, 5, 6. So I made 1, 2, 3, 4, 5, 6. At position number 3 there is ketone, so there is ketone. At position number 5 you are having this vinyl group, so vinyl group is there, and then alcohol is there, CH2OH, that CH2OH is there. But because this was above the plane, so this is toward the viewer, this was below the plane, so it is away from the viewer. Similarly, this H is exo towards the viewer, so this H will be towards the viewer, which I have not shown because you need not show hydrogen. And this one is below the plane, rather you can say endo, it is away from the viewer, so it is away from the viewer in the product also. So that's what is the answer. The answer is B. Next question. The number of carbonyl groups present in the following reaction sequences. So you are having this interesting molecule. This part you can see, this is anhydride. When two acid reacts and water is lost, you get anhydride. So how is anhydride formed? Something like you are having C double bond O, OH, okay, and you are having here also R, C double bond O, and you are having OH. So basically water is lost and you are getting what you get is R, C double bond O, C double bond O, R. That's why it is called anhydride. Anhydride means water is lost. So basically this is anhydride and you are having ketone and you are having alkene, and this is ketone, this is ketone. They are asking at the end how many ketones are left, and you are reacting with ozone. Ozonolysis you are doing in presence of H2O2 followed by H3O plus, okay, followed by H3O plus, right. So we know ozonolysis, what it does is basically cleaves the double bond and puts it breaks it and puts oxygen on both the places, right? And if hydrogen is there, it remains hydrogen. If R is there, it remains R. But for that you have to put ozone followed by zinc and water or dimethyl sulfide. But if you are putting H2O2, if it at the end at the end of the ozonolysis, if you are getting aldehyde gets oxidized to acid. If ketone is there, ketone you cannot oxidize. Why? Because ketone, you see carbon bond is there. So this is carbon bond, this is carbon bond. It will not get oxidized. But if you have something like some aldehyde, and then which you get after ozonolysis, then CH bond is weak, you can break it, so you can oxidize in presence of H2O2, so it becomes COOH, right? So if ketone is there, nothing changes after ozonolysis followed by H2O2, but if aldehyde is there, aldehyde gets oxidized to acid. So let us look at the reaction. It should be very, very simple question. So that's what happens. See here, if any aldehyde or ketone, this knowingly I have made it like this. So one plus H is there and other plus both are R, right? in this side of the alkene, one is R, one is H. This side you are having R prime and R double prime. So when you are breaking, you put two oxygens. So you are putting oxygen here and oxygen here. So remove this oxygen for time being. So you are getting aldehyde, and this part you are getting ketone. Now ketone you cannot oxidize, but aldehyde will get oxidized and you will get acid. So same thing is happening here, but here both carbons you are having hydrogen. So both of this part will become acid. Now it is saying how many carbonyl groups are there. So this is acid, of course this is not carbonyl. This is carbonyl, this is carbonyl, this is carbonyl, this is carbonyl. This is not carbonyl, this is part of anhydride, right? So the answer should be 4. Okay. Moving to the last question. The question says, the strongest band observed in IR spectrum of the final product formed in the following reaction approximately at dash into 100 per centimeter. Okay. So basically first you have to find out what is the product, and then you should know IR value of it. So when you look at this molecule and heat, very clearly first thought should come to your mind is it will be 3,3 sigma tropic shift, and we have to see it is cope or oxycope. So 3,3 sigma tropic shift, what happens? 3,3 sigma tropic shift, basically you break the bond and form the bond. So in the transition state 6 electrons are involved, 3 plus 3 is 6, and therefore it happens in thermal condition. Wherever you break, you start you start giving the numbering 1, and you have to go to the end. Wherever bond forms, that number what you had initially given, that's the number which it gets. So basically how the reaction will happen is this bond will break, this comes here, this comes here, this comes here, and you are getting. So because you are breaking here, you start counting from both sides. 1, 2, 3. Similarly here 1, 2, 3. So this comes here, this comes here, this comes here. So you get this bond, and you are having CS3OH, and here you are having CS3 and OH, right? So bond formed here. What was the number here? 3 and 3, and therefore numbering is 3,3 sigma tropic shift. Now you are having enol. Enol will never remain like enol. They will always tautomerize to give you ketone, right? So here also this happens. So OH, this comes here, this comes here, and you get ketone. Similarly this moves here, and this moves here, and you get ketone. So ketone, aldehyde, all of them give around 1710 per centimeter. So they asked into 100, so it is times 100, so it is 17 times 100 per centimeter. That's it for today. Thank you.